Hello everybody, welcome back to the Gregorius Maths video. This video is for my Math Society because I lost my composure when I was doing this topic, on that fateful Wednesday lunchtime, so I thought, okay, I'll make up for it with a video on the topic and the accompanying notes. So I'll put the notes in the description of this video in case the regular Gregorius Maths viewer wants to see the notes as well. And actually this is quite an interesting topic, regardless of whether you're a student of the school I go to or just a regular Gregorius Maths viewer. Because in this video I'm going to be motivating sort of number theoretically, at least. I think there's multiple different sort of motivations. You've got the sort of abstract algebra motivation for what an ideal is, but okay, this time I'm going to be going for the sort of concrete number theoretical motivation for ideals. And the example I'm going to use is how ideals can fix unique factorization. So, and this works out perfectly because I've actually done a video on this topic on my channel. We've seen before in Math Society that if we want to look at theorems, sort of if we want to see properties of the integers, sometimes it's helpful to travel to sets that are bigger than the integers. So last time we saw how going to the Gaussian integers was helpful. We do some stuff over here, we look at what happens in the Gaussian integers, and then with our new results in the Gaussian integers, we travel back to the integers and we apply our new results from here to the integers, and that allows us to prove stuff. And an example of this actually happening is showing that every prime which is equivalent to 1 mod 4 can be written as the sum of two squares. And this is actually a really surprising, really nice result, and it's kind of an advertisement for why algebraic number theory is cool. And I'll link the video where I explain this in the description, but okay. Now that we've established that looking at sets which are bigger than the integers is useful, now why don't we actually just study them and look at what properties they have. So in today's video we're going to be specifically looking at a set called the integers adjoin square root minus 5. And these are just numbers of the form a plus b root minus 5, where a and b are integers. So for example, 2 is an example, 2 plus 3 root minus 5, 7 root minus 5 is an example. All of these are examples, 0, whatever. Okay, so we're going to study this set today. Now, what's one property that is sort of fundamental to the integers is the property that we can uniquely factor every integer as a product of prime numbers. So, for example, 6. 6 is 2 times 3. Wonderful, unique factorization of 6. But now that we're working within this bigger set here, we have an issue, because 6 is also equal to 1 plus root minus 5 times by 1 minus root minus 5, by difference of two squares. And if you check via, a little argument with norms and stuff, you can see that all of these elements are irreducible. And so we have an issue because we have two distinctly different prime factorizations of the number 6. Now this is very alarming, this is bad. We don't want this to happen. So we need to fix this, promptly, we need to really like figure out a way to get back on track here, because things are starting to get out of hand now. So how do we do this? Well, Kumer, or however you pronounce the name, actually I'm going to get a fresh pen for this. He said, okay, well, you know what would be nice, guys? What would be nice is if we had numbers A1, A2, A3, A4, such that 2, oh no, this is a terrible pen. Okay, never mind. We can let's go back to this. It's a good pen, actually. It's a really good pen. It's just too thin for the board. So such that 2 is equal to A1, A2, 3 is equal to A3, A4, and 1 plus root minus 5 is equal to A1, A3, 1 minus root minus 5 equals A2, A4. And, well, why would this solve all of our issues? Well, this would solve all of our issues because then these factorizations wouldn't be different. This would just be A1, A2, this would just be A3, A4, this would just be A1, A3, and this would just be A2, A4, and you can see here that these factorizations would now actually just be the same, they would just be rearranged, and that's fine. Now we can have some rearrangements, that's okay. But, okay, these numbers don't really exist, so why is this helpful to consider such numbers, if they existed? Well, let's push this further. Let's say, okay, these numbers exist. What property does it have? Well, A1. A1 has the property that any multiple of A1 is also, any multiple of 2 is also a multiple of A1. So, we have let me not use R. 2A. For any element of our integers adjoining the square root minus 5, if we, any multiple of 2 is also a multiple of A1. But we also have that any multiple of 1 plus root minus 5 is also a multiple of A1. And if we add 2 multiples of A1, we're going to get another multiple of A1. So 2A plus 1 plus root minus 5b should also be a multiple of A1. And what Dedekind, his key insight was, let's not consider A1 as a number. Let's consider it as a set. And indeed, we'll consider it to be the set of all elements of the form 2A plus 1 plus root minus 5b, where A and B are elements of our thing. The integers adjoin root minus 5. Now, okay, why is considering sets, like, we're just making things more complicated for ourselves. You know, we've seen that our unique factorization fails, and suddenly we're descending into madness. Well, slow down. There's no need for such a negative attitude. Let's let Dedekind, let's let him proceed. Let him cook, as the new generation would say. Anyway, okay. So, if we just pick some random numbers, some general elements A and B of the integers adjoin root minus 5, then one random element of this set would be 2 times A1 plus A2 root minus 5 plus 1 plus root minus 5 times by B1 plus B2 root minus 5. Okay? This is just what a general element of this set looks like. If we expand this, what we get is 2A1 plus B1 plus minus 5B2 plus 2A2 plus b1 plus b2 root minus 5, like so. So what can we say where all of these a1, b1 and stuff are integers? So what can we say about this? Well, the first thing we can say about these two integers here, like the coefficient of root minus 5 and the sort of constant here, is they are equivalent mod 2. Why can I say this? Well, adding 2a1 and adding 2a2 is going to do nothing. Okay? Because if you add a multiple of 2 to a number, that's not going to change the remainder when you divide by 2. So we can ignore these. The b1s are the same, and the b2s differ by 6 lots of b2. But because they differ by 6 b2, well, 6 b2 is always going to be even. So if two numbers differ by an even number, they're going to have the same remainder when you divide by 2. Okay? So, first thing we can say about this set is a plus b root minus 5, if we write an element of this set like this, where a and b are integers, then a and b have to have the same remainder when you divide by 2. But also note that if we set b1 and b2 to be 0 for a second, then we get 2a1 plus 2a2 root minus 5. So a1 and a2 don't depend on each other, so we could get any combination of even numbers we want. Similarly, if we let b1 be 1 and a1 and a2 and b2 is 0, then we get 2a1 plus 1 and 2a2 plus 1. And that could also be any combination of odd numbers that we want. And so indeed, a1 is actually precisely equal to the set of all a plus b root minus 5, where a and b are integers, such that, a and b have the same remainder mod 2, and a and b are integers. Okay, so like 1 plus 3 root minus 5, or we could have 2 plus 4 root minus 5, or we could have like 6 plus 94 root minus 5, or anything like this. These would all be elements of this set. And actually, if we consider a2, a2, which is equal to, well, it's got to be a multiple of 2, it's got to contain the multiples of 2, so 2a, plus, and now 1 minus root minus 5, so 1 minus root minus 5, b, where a and b are 5 like this. If you expand it out with very similar reasoning, you can actually see that these two sets are also the same. So, okay, we have a1 is equal to a2. Now, if we look at a3 and a4 don't enjoy the same property. So what I'm going to do is I'm going to write out our sets that we're considering now. So instead of considering numbers, we're considering sets. A1, okay, let me use green. A1 equals, sorry, not square root, what am I doing? The set of all 2a plus 1 plus root minus 5b, where a and b are elements of the integers adjoin root square, blah blah blah. Okay, and this also happens to be equal to a2. A3 is equal to, well, it's got to contain the set of all multiples of 3 and 1 plus root minus 5. So it's the set of all 3a plus 1 plus root minus 5b, where again a and b are elements of the integers adjoin the square root minus 5. And a4 is going to be 3a plus 1 minus root minus 5b, where again a and b are elements of the integers adjoining square root minus 5. Okay, so, okay, cool, we've got these sets, and we sort of understand what the elements of these sets look like. You know, we saw a1 equals a2, okay. We're still just talking about sets, but how is this helping us with unique factorization? How? You know, we're just considering sets. We're doing some nice expanding, you know, we're practicing our algebra skills, but how on earth are these random sets going to help us with unique factorization? Well, here's where the concept of an ideal comes in. So, the ideal generated, so we're going to introduce a sort of notion here. The ideal generated by some A within our specific set here is just the set of all multiples of A. So r times A, where r is just any integer adjoin root minus 5, like this. So this is the ideal generated by A. Now, what we're gonna look at here is, instead of saying 6 is equal to 2 times 3, we say that the ideal generated by 6. So now we look at all the multiples of 6 at once is equal to the ideal generated by 2, so that all of the multiples of 2 times all the multiples of 3, and this is also equal to the set of all multiples of 1 plus root minus 5 times the set of all multiples of 1 minus root minus 5. Okay, how have we fixed things? Well, now our ideal numbers come into play, because our ideal numbers, we wanted them to satisfy 2 is equal to a1, a2, 3 is equal to a3, a4, so that it would fix things. So what I'm claiming is that these ideals will fix this statement here, where we expand our domain of thinking from just, like the boring statement 6 equals 2 times 3 equals 1 plus root minus 5 times by 1 minus root minus 5. We expand from here to the set of all multiples of 6 is equal to the set of all multiples of 2 times the set of all multiples of 3. If we expand our domain of thinking from here to here, suddenly these sets are going to come in incredibly clutch, if I may use some youthful slang. So this set here, we don't just have one generator, so this is just the multiples of A. But this ideal here is the multiples of 2 plus the multiples of 1 plus root minus 5. So we'll call A1 is equal to the ideal generated by both 2 and 1 plus root minus 5. And also note that this is equal to A2. Okay. A3, what are the generators for A3? 3 and 1 plus root minus 5. And A4 is equal to 3, 1 minus root minus 5. Like so. Okay, now, what I'm going to say is, the way we multiply these ideals is we just multiply the generators. So, for example, if we did A1 times A2, that would just be A1 squared. So if you do 2, 1, so this is just FOIL. So if we do A1, A2, sorry, I'm just going to write A1 squared. If we do A1 squared, this is the ideal generated by 4, then, yeah, 4 4 plus 4 root minus 5, and this thing is 1 minus 4 plus 2 root minus 5, I think. Like so. Oh, okay. So that's a1 squared is generated by those three elements. How am I gonna... Okay. So, oh, sorry. No. Sorry, my bad. We get 4 different elements here. So, we get 4. We get 2 plus 2 root minus 5. 2 plus 2 root minus 5. And 4 plus 2 root minus 5, I believe. Plus 2 root minus 5. Yeah. Because we do 2 times 2. We do 2 times 1 plus root minus 5. Then we do 2 times 1 plus root minus 5. And then we do 1 plus root minus 5 times by itself. Which should be that, if I haven't done the algebra wrong. And if you write out a general element of this, it's going to be 4a plus 2 plus 2 root minus 5b plus 2 plus 2 root minus 5c plus 4 plus 2 root minus 5d. Well, we can see that these are all going to be divisible by 2. So our a1 squared is a subset of the ideal generated by 2. But also, we can see, if we just let, if we were to expand everything, what we would see is that we can, find a combination of integers such that 2 is contained in a1 squared. But if 2 is contained in a1 squared, then all the multiples of 2 must also be in a1 squared. And so we, in fact, can turn this subset into a strict equality. And so this right here is a1 squared. And if you do the same sort of expanding out the brackets process, you will find that 3 is a3, a4. This is a1, a3. This is a1, a4. And now, boom goes the dynamite, because we've just fixed prime factorization. And there is a very real sense in which these ideals here are indeed prime ideals. And in fact, considering expanding our domain of thinking from numbers to ideals restores prime factorization. And in this way we can motivate the notion of ideals further. And maybe I'll make a separate video where I delve into the nitty-gritty, but I just wanted to make this video for Math Society because this is the talk that I wanted to give, but I sort of failed on the day. So yeah, here it is. And yeah, hope you enjoyed. Yeah, it's pretty cool, so good day.